you have this file. It's called Notched Bars S2026. So please download this and save this to a folder where you have access to write, okay? Because you'll need to later save this. So if you save it in default folder, you may not have access to write. So just make sure you are saving it, or you can save it to your OneDrive as well, okay? Then in addition to this, you also have these files which are giving you a report template that we will try to complete based on the data that you use. Now, the report already has the data for my case filled in, okay? So I can take you along through this. So the one in the red, that's my data that I will be using. So the purpose of the analysis today is to teach you how to carry out finite element analysis using Solidworks. So we will take this same example which we covered in the last lecture before the mid, okay? So I covered this example with you, and I did the hand calculations with you for this problem. So we had a notched bar on which an axial load was being applied, and the dimensions of the bar are shown to you. So in the lecture, I took you with me to solve this problem using hand calculations for different values of stress, such as gross stress as well as net stress. And then I also introduced to you and I also calculated the total change of length as well as the strain. And after that, I also calculated basically the stress concentration factor using the concept of the stress concentration factor charts. But today we are going to use a different approach, and we are going to use finite element analysis to essentially solve the same problem. But then later on, you can choose literally any of these groups. I don't mind, okay? And you can do the problem for one of these materials and one of the force given over here, so that you basically get practice. The main idea is to use this for practice, because I'm not asking you to submit this lab tutorial, because at the end of the day I will be assessing you based on the how you apply this analysis method in your project, okay? Because the project is really the assessment point. So here the main purpose is to learn and understand and practice. So in order to, I think I've already gone through the basis of what finite element analysis is in the class during the lecture session. So today we are going to use one of the software tools. Now, like I said in the class, there are many software tools that can be used to to carry out finite element analysis. In this case, the tool that we are using is Solidworks. Those of you who have studied Solidworks will already be familiar with the software, okay? So that is my general recommendation, that people who have done Solidworks should take this course. But even if you have not done Solidworks, we will not focus too much on part modeling. Rather, we will be focusing on the analysis, because primarily Solidworks is a part modeling software, okay? So it allows you to model different parts, different geometries, as well as full machine components, and create their 2D as well as 3D drawings as well as solid models. So for our analysis, we are assuming that the part file is already available. That is why on the D2L, I have already uploaded this part file, which I asked you to download. So this file, notch bar S2026. So please download this, and once you have downloaded it, you can simply open the file. I already actually have the file open. I don't need to really open it again, but just to show you. So you have to click on the open button and then browse to where you have saved the file. Click on the file name and click open, and that will open up this file for you, okay? Now once this file is open, you have this pane which is showing you the different operations that are possible, okay? Typically, when you are drawing the model geometry, you will be either in the sketch or the features plane. If you are first trying to make a 2D sketch, normally you start with a 2D sketch. So for example, we would have started by one of the sides and then used a operation such as extrusion to basically create this part. But right now the part is already created for you, and it has the same geometry units as it has the same dimensions as given in the example problem. Now, first thing you should do is to check whether the system of units is correct. So I will do everything in millimeter, grams and seconds in this example. Okay, so because it's a small part, so it's better to stay with millimeters. Now with that settled, I can now proceed with the steps of analysis. Now keep this in mind, I have also uploaded on the D2L this step-by-step guide. Okay, so if you get lost or you want to consult later when you are doing your project, you can download this guide, and this is basically a book chapter which you can use to replicate the analysis task that I have given. The main difference between this step-by-step guide and the analysis that I will be doing is that I have used SI units, whereas in this example the inch-pound system of units is used. Okay, other than that it is mainly same. Secondly, because this is 2020, I think 1 or 2023 version in the book, therefore there is one little option different which I will explain to you as we proceed. That's the option of how you change the mesh quality. Other than that, I don't think there are any differences. So let me now explain. So basically, for any finite element analysis, there are 3 stages. The first stage is called as pre-processing. Then you have the post-processing, and then the post-processing. The pre-processing means basically, first of all, defining your model geometry. So like in this case, part of the pre-processing has already been done for you because you have already been given the part file. Okay, so if you have not been given the part file, then you have to start by actually drawing the sketch and then creating the solid model, and then that will be part of your pre-processing. But that's just the first part of the pre-processing. Many times the actual features that we draw have too many details. They are not always necessary for analysis purpose. So for example, even in this part that I have shown you over here, if you look at it closely, if I zoom in, right, you can see that the part ends are curved over here, for example, right? Now in a real part, if this was used, yes, maybe the ends will be curved to make it smooth so that people do not hurt their hands while holding it, right? But from the point of view of analysis, these curved portions are not adding any new information, right? So in fact, these will only make the analysis more complicated. Okay, so just like for our hand calculations, we always take some simplifying assumptions. So in FEA we can also take some simplifying assumptions. So in this case, my first simplifying assumption will be that I will get rid of these fillets. Okay, now to get rid of these fillets, basically all you have to do is to select each of the fillet and then right click and then click on suppress option over here, right? So if you click on suppress option over here, then you will be able to get rid of this. Now because in most of the time we already have, so you can do this individually, or you can just press control button and then click and then select all these features, right? And then you can do it together as well. Okay, so that's the other way of doing it. Then there is also a third way of doing it, and that is if you already have a group made. Like in my case, I have the fillet already being defined in this group when I was making the part. So I had made it already there by this name. So now I can just simply select this, right click on it and then click on suppress. And this will basically remove the fillets from it. And now you can see the part has got straight edges. Okay, this will make the meshing of our part easier. Now keep this in mind that this feature, the feature of the notch, is not something that we can simplify. Why? Because this will affect our results. This will affect our values of the stresses and the strain, and therefore the strength of the part. So this is not something that we want to simplify, and we will keep this feature, right? So so we have to be careful about what we are simplifying and what we are not simplifying. So now when this has been simplified, what you can do is the next step is to basically start as what we call as a simulation study. Okay, so you have to go on to the simulation tab. Can you see it on the top where my mouse is right now? Right, so it says simulation. So if you click on this, do you want me to cast it on your computers directly? Will it make it easy to see? Okay, let me do that. Let me cast.
Is it okay if our software doesn't look exactly like yours?
Yeah, because your version may be slightly different than mine. So,
2026, there is a difference.
sorry?
2025, 2026 is different.
Maybe slight difference in interface,
Yours is
but the
26.
functionality will not be different.
Okay.
Okay, I think mine is 23, unfortunately.
Yeah, that's why,
Okay, that's
we,
why.
We are working
We are
on
25.
Okay, so I can later on come to your individual desk if you get stuck, but I don't think there is any big difference there in terms of these features that we are trying to
The feature
use.
is the same, but the place is like simulation for you. It's on the left. We are on the far right. The left side bar is different for us, a little different. But
Okay.
it's the same features.
I can come and have a look at that. Okay, but the feature will be the same. It may be just the small placement which is different. Okay, so I'll now cast it onto your screen so you can see it clearly. Okay, now having done this, so now I will go on to the simulation tab. By the way, the way these bars are arranged, a lot of these things can be customized as well according to your needs. Okay, they don't need to be always in the same place. Every person can also arrange a lot of these in their own way. One easier way is that if you forget any of the commands, you can always put on the top here, and then you start typing and it will give you the options. Okay, so that's the easiest way. So whenever I forget a command, I use this to search for it. Okay, from the search bar. So now once I have clicked on the simulation, I have the option over here. Can you see on this side, study option? Okay, so I have to click on this study option to start a new study. Okay, because every analysis in SolidWorks is called as a simulation study. Okay, so you have to click on this to create a new study first of all before you can solve and get any results. Now within the study option, there are, you can see, almost like 7 or 8 different options. Yeah, the first option over here is static, then you have frequency, then you have topology, then you have design study, then you have thermal, buckling, fatigue, nonlinear, linear dynamic, drop test, and pressure vessel design. So these are all different types of simulation tools which can be used depending on the requirement. Okay, now each tool will have a different analysis methodology, so the underlying equations may be different. So for example, when we are using the buckling analysis over here in FEA, it will be basically dealing with Euler buckling analysis, okay, or eigenvalue buckling analysis as we call it. But in your case, in this course, we have solely focused on static based analysis, right? That was our first assumption. We were assuming the static equilibrium to be always applicable. Therefore, in my case, I will go for general simulation of the static type, and that is already by default selected. If for any reason this is not selected, then just simply clicking on it will select the option. And then in the name, you can give this study a name of your choice. In the template, I have given them different names depending on what we are trying to do. So for example, in my first case, I am calling the study because I will run the analysis a number of different times. Okay, so my first case, I am calling it as draft mesh default size. Okay, so I'm calling my first study as draft mesh default size. If you want to give it a different name, you can, but then make sure you remember that what name you have given, so that when you are writing the report, you understand which case you are comparing. So my first case is draft mesh default size. So this is my name for the first study. Keep this in mind, naming will not activate any options, it is just a name. Okay, to activate the options of the study, you have to actually click on the certain dialog boxes to actually activate them. So now after this, I will click on this OK button on the top, and this is going to set up our initial study option. Can you see here on the right, on the left hand side, you have got the a pane has appeared. Okay, a new window pane has appeared, and this window pane is showing you the name of the study, which is draft mesh default size, and it is also indicating that the part has already been simplified. And then there is the name of your part, notch bar S2026. Okay, so this is the study option for this case. Now within this study, there are several steps. Okay, now depending on what you are trying to achieve, you will have to go through different steps, but at least 3 steps are going to be always there. Okay, the 3 steps which will always be there are assigning the fixtures, assigning the external loads, and creating a mesh. So these 3 steps will always be there for the pre-processing. You cannot run a simulation without it. If your part is more complex, and let's say you have got more than one part, so for example there is a pin connecting a part with another part, then you may also have to define connections. Okay, in our case we don't have to define connections because it's a single part that we are trying to model. Okay, even in a more complicated assembly, think about the example that we did in the midterm exam, right? So in that example, you had a rigid bar and then a bar in which you were interested. So in that case, if you can use the statics to initially calculate the force in the bar, then you don't have to model the entire assembly. Rather, you can just model the bar in which you are interested. Okay, so how, because at the end of the day, the more complicated the part is, the more computational power it will need to solve. So we have to be careful about what we model and what we do not model in the software. Right. So now the first step for the preprocessor, sorry, I think I said 3 steps, but there are actually 4 things that are always going to be there. So I said that there will be fixtures, there will be loads, there will be mesh. But what I forgot to say was that there will always be material assignment as well. Because right now the geometry is just, lines. It's just some surfaces. It's basically a point data. It doesn't have any material property assigned to it. And without material property, the software cannot solve the analysis. Okay, so that's the first thing that we will be doing. And to do that, I will right click on this, and I will on my part file, and I will say apply edit material. So when I click on apply edit material, I have this option, and I can choose from the database of materials present within Solidworks. Okay, so in this case, the material which I can choose is AISI 1020 steel, because this is what I have mentioned here in the input table, right? So I have said my material is AISI 1020 steel. In your case, if you have chosen, let's say, group B or C, then you will have a different steel that you can use. Okay, and similarly you can choose any other material. Now for your project, you may be first finding the material based on Granta, and then you can find the same material. If you can't find exactly the same material, you can find a material which has properties closer to that. Okay, the third option is that you can actually also define what we call as a custom material here. Okay, and then input that properties. But for now, I will keep things simple, and I will use a material from within the database, and that is AISI 1020 steel. Okay, now here you can change the units to whatever you want to, basically, and to make it easy for you to read. And you can see here the default properties like elastic modulus, Poisson ratio, mass density, yield strength of the material are already given to you in this. So all you have to do is click on apply, and this will basically apply the properties to the material, to the part that you have selected. If you have more than one part, then you have to do the process separately for each part. Okay, so now here you can just click on close, and this will assign the material. How do you know that the part has already been assigned the properties? By just looking at this, and you can see after the part name it says the name of the material, and this tells you what is the material that we are using in this simulation. Now, so the first main step has been completed. Now the next step in this case is to apply the fixed condition, basically, because the part needs to be fixed from some side. Let's in our case it is fixed from one end here, okay, and the type of the boundary condition will also affect the results. But in this case the boundary condition is that it is completely fixed, okay, meaning that it's a built-in boundary condition. Okay, so to apply this boundary condition, again a lot of these things will come with experience, you to understand which boundary condition is appropriate in which scenario. But for now I'm using the simplest condition, which is fixed geometry. Okay, so I will right click on the fixtures icon, and after right clicking on the fixture icon I click on fixed geometry. Now when I click on fixed geometry, it opens up this box. I now have to select the surface which I want to fix. So in this case, if I rotate my part, okay, and I'm not going to fully rotate it, rather I will just simply make sure that the part that I face that I want to, so this is the face that I want to fix. Okay, so yeah, they are same, but because then one is will be positive x, will other will be negative x, so it's better to fix the face which is at 0 right now. But again, the result interpretation can be slightly different depending on how you fix it, but otherwise the part is going to be fixed, can be fixed from either end. Okay, in my case I'm fixing it where the origin is. Okay, so it is this face, and I can fix the whole surface, and I can also fix the edges. Now whether you can see here, anything that I select comes up in this window over here, so it tells me that this is something that I have selected. In addition to the surfaces, I will also click on edges. Again, in this simulation, whether I select the edges or not will not make a huge difference, but in more complicated simulations these choices will also affect. Okay, so you should try to mimic the reality as close as possible, but then again be mindful that you know of your simplifying assumptions. So in this particular case, once I am happy with the selection, I can click on the green tick on the top, okay, and that will allow me to apply the boundary condition. And you can see these green arrows are showing me that the displacement boundary condition. What does it physically mean? From a mathematical sense, inside what's happening is that the software is setting up u1, u2 and u3 equal to 0, where u's are the displacement along x-axis, y-axis and z-axis, right? So it is setting up all of those displacements as well as rotational degree of freedom. If the body has that, then it will set those to 0, and this is a completely fixed boundary condition. In other cases, you may have to keep some freedom. For example, you may want to allow for rotation, right? If we have time to do the torsion, then I can do that in that example, but in this case our condition is that it is completely fixed. The next step is to apply the load. Again, the load can be applied in many different ways, but in this case the way we are applying the load in the given problem is that it is a point force. Okay, so it's a point force acting on the face over here, on the free face. Okay, so that's what we will do, and basically we will say go on to the external load option, right click on it and click on force. So once we click on the force, again we have to choose the surface. So in this case it's not this surface, rather it is the front surface, which is free surface over here. The direction of the arrows tell you that the load is being applied in a compressive manner, okay, which is not correct. Right now we need the load to be applied in a tensile manner. So to do this, I can either manually input the load as a negative quantity, or I can just simply say reverse direction. This is the preferred option because this will allow for a more consistent display of results later. Now, underneath you have the option of per item or the total. In this case, because there is only one surface on which you are applying the load, therefore it doesn't matter, right? So per item is there. But if you have more than one surfaces, then you have to decide whether you want it per item or the total load that you are specifying. So in this particular case, the system of load application is SI, so it is in newtons, and the magnitude of the load, I will take it from the example. So because I want to compare it later with my hand calculation, so I am keeping exactly the same values as the ones that I used in my hand calculation. So this is 26,650 Newton for me, and if you are following one of these groups, you can take one of these load cases. So for me this is 26,650 Newtons. So once this is done, we have completed the three main processes of pre-processing, okay. The only step left now in the pre-processing is what we call as meshing, okay. So I will continue with that. I will just simply quickly pause my recording here and come to you to see if you have been able to complete the process so far, and then I will proceed with meshing. The basic model setup has been complete. Now the main thing is to mesh it, right? And remember, I explained to you what meshing means, right? Meshing means dividing it or discretizing it into smaller units in which you can assume a certain functional distribution of your field variable. In this case, our field variable is basically the strain, right? And the strain field variable is linked to stress, and it's also linked basically on one side to displacement and on the other side through stress to the force, right? And that will allow the system to solve for it. And within, now how you discretize it will affect your results, meaning how many number of subdivisions that you create or what type of element you use, because inside each element has certain assumed behavior. So let's now first of all try to mesh it with the simplest type of element that is there. So we will go and we will say right click on it and we'll say create mesh, okay. So when I say create mesh, it gives me certain options. Now many times the student would just simply blindly go and apply this option. Yes, it will work, but then you do not understand how the results are changing. That's why I want you to pay special attention to this. So you have the mesh quality option here, okay, the mesh quality option on the top. Now I think in the old version, in the PDF that I have uploaded on the D2L for step-by-step instruction, this step is slightly different, okay. In the old version, the mesh options are in a slightly different location, but for our version that you are using, the mesh option is right next to the definition, okay. Now you have two options, either to use a high quality mesh or use what we call as a draft quality mesh, okay. Now the draft quality mesh basically reduces the number of internal points on which calculations are being done. Now I'm deliberately keeping the mathematical description very simple because I have not explained to you the maths behind it, right. In simple words, a draft quality mesh will only have the number of nodes equal to your number of computational points essentially on the element, and that is something that I will explain to you in a few minutes. So with the advantage of using a draft quality mesh will be that you can very quickly run the analysis to get a feel of the results. So think about it, if you are trying to model a full aircraft wing, that's a huge part. If you start doing it with a high quality mesh, then the chances are your computer will crash even before you start getting good results, right? So you do a what if analysis, what kind of analysis, very quickly using draft mesh. So this is what we are going to do, and I will select the draft mesh first of all, and in the definition I can either move the bar to coarse or towards the fine side or keep it in the middle. What it changes is if you click this drop down button, you can see the mesh parameters, and if I change this on the fine side, you can see this size has changed, right, to 2.13. This size will be relative to your part size, okay, and Solidworks is automatically adjusting it. On the coarse side, for this part size, my mesh can go as high as 8.5, okay. Now if your part size was bigger, these numbers can also be different, but they will be a relative factor of your part size. Now if you click on reset the curve, it will come into middle. Now within these there are certain options, like there right now you have the blended curvature is selected by default, okay. You have other options like curvature based, and you have got the standard mesh. For all of my simulations today, I will be using standard mesh. The blended curvature and curvature based meshes are more useful if you've got more intricate geometry, you know, which is changing in the space in curved manner significantly, then those can be more useful. For us, the standard mesh will be an easier option to deal with. So we'll click on the standard mesh, and I will keep it on the default size, which is in the middle, right? If you have moved it out of the middle, then just simply click on reset and it will go back to the default size. That is why when I was naming the study, I called it as default size and draft mesh, okay. So draft mesh and default size, so it is indicating what type of mesh it is, okay. Now once I have done this, I can now click on the OK button to basically to show you the mesh, and you can see very quickly Solidworks has created this discretization on our part. So these are basically the units on which it is going to have an assumed stress distribution function, and for using which it is going to solve the finite element analysis. Now we will note down certain key information about our mesh so that we can compare the results later, okay. This thing which I am going to do, this is called as mesh convergence study. So basically in finite element analysis, as we change the mesh, the results will change, and we need to have an idea about when the results have suitably converged to a unique value, okay. So I will take you through this process step by step, but for the first mesh, what I have to do is I have to go into the summary option, or actually if I use detail, I think it's easier to read. So if you go into the detail option, you can see this table, right? The table lists all the key things about your mesh. So it is saying that it is a draft mesh, it is telling you that the type of mesh is standard, right? And it is also giving you an important information about the element size as well as the nodes. So how many nodes are there? 1606 nodes, and the number of elements is 6444. So what does it mean? It means that these, you know, these triangles that you are seeing, so it has got these 6444 of these wedges. So I won't call them triangle because they're in 3D, so it's a wedge, right? So it's got these wedge elements 6444. The number of nodes in this case is smaller than the number of the actual wedges. Why? Because you see a lot of these nodes will be common. So what are the nodes? So for example, this will be a node, right, over here, which is connecting point, basically on the vertices. And again, later on I will show you other elements that will have nodes on other points as well, okay, not just the vertices. So each vertex in this case is a node, okay, but because a lot of nodes are going to be shared, meaning they are going to be common between, so let's say this node is common between this element, this element, this element, this element, this element, and this element, so that's why the total number of nodes is less. Now why the number of nodes is important? The actual calculation, if you remember, I wrote down that matrix F is equal to KU, right? And I said that there is F1, F2, and you know F3, F4, and then on the other side there is displacement 1, displacement. the number of equations in the finite element analysis of this type will be dependent on number of nodes. Okay, so basically it will write a discrete equation for each of these nodes. Okay, so that's why the computer internally will be solving 1606 equations to get the answer. Okay, so let's now quickly note down this information. I've already done that in my case for you, but if you are recording the information, then you can actually do that by downloading the Word version of the same document and writing down your own numbers so that you can later create a graph as well. Okay, so let me quickly show you the place where I will be recording this data, noting down this data. Okay, so I am noting down this data in this table. Okay, so on the top you've got number of nodes and then you've got number of elements. So last time when I run this analysis, maybe the settings were slightly different, therefore I have got slightly different number of nodes and elements. I can actually update this now. So this is how much today? It is 1606 nodes. Okay, so it is 1606 nodes. And number of elements in this case is 6444. Okay, so I will delete the rest of the data as well for now so that I can record it later. Okay, so now once I have done this, yes.
Giving me an error. What's wrong? I can't get this on it. Mesh information is not current. Model might have been updated or mesh element size tolerance was modified.
So maybe you modified it, so just remesh it. Okay, so just remesh it.
Should I delete it?
No, just go on to the create mesh again. Okay,
Create mesh.
yeah, and then just select the options. Okay,
Didn't change anything else, right?
Yeah.
Mesh.
okay.
Okay.
So now once you have done the meshing, your pre-processing is now complete. Okay, your pre-processing is complete. Now what you need to do is let the computer solve it, and that's basically called as processing phase. Okay, so you basically submit it for analysis. Now again, because we have got very powerful computers these days, so this kind of mesh can be solved in a few seconds. Okay, so but again there is a limitation to computational power, and depending on how big the problem is, the time can be more or less. So now to run the analysis or to actually submit it for analysis, you have to click on this option of run. Okay, so if you click run now, it will solve, and you can see after solving it has given you certain default results. Okay, now the default results which it is showing to you right now will not make sense to you. Why? Because look, first of all you need to understand what quantity it is plotting, so always take note of that. So right now the quantity is here, which quantity? 1 Mises stress, right? 1 Mises or 1 Mises stress. Have you studied this in the course so far? Our course, strength of material? No, right?
No.
So that means it is not something that I have covered so far, but I will be covering it in the next few lectures. Okay, so for now I can ignore this for a few minutes, but I will come back to it and I'll explain it to you later, because that will then link to our next sessions hopefully. So then you have also got this option of displacement and strain by default. Now these are just the default plots that are there. Okay, Now what you can do is you can always plot the quantities that are of more interest to you. Okay, so for example, for me, I need to plot, for example, the sigma x, isn't it? The normal stress along the x-axis, right? So can I plot that through software? Yes, let us do that. So to do that, I will right click on the results. I will go into define stress plot. Okay, I will go into define stress plot, and I will go and I will select from the display option normal stress along x-axis. Now keep this in mind. If what is the meaning of x, y and z depends on how you have drawn the geometry, right? So always look at this legend. Okay, so this will always tell you which axis, so that you select the correct component. Okay, so right now my x component is the one that I'm interested. I will select the units as megapascal to make it easy for me to read, and then I can have either automatic scale factor or true scale factor. Now right now it is showing you a very high automatic scale factor of 347. Okay, I will initially plot it with this automatic to show you why it's not suitable in this case, and then I will correct it to true scale factor later on. Okay, now there are also other options in the chart options like show minimum, show maximum. Okay, so I will also select them. Similarly, in the unit system, I would like a floating point representation with 3 decimal places right now. Okay, or even for the stress I can go for 2 decimal places is also enough, because it's a big unit of megapascal that I'm selecting. Okay, now with these done, I can click on the green tick to plot my stress, and now you can see here that the stresses have been plotted, and you are now seeing some numbers where the minimum is coming out as 13.98, the maximum is coming out as 108.51, and it is actually, the computer is telling you that it is in this location next to the notch, right? Similarly, this graph on the side, this legend on the side is also showing you those maximum and minimum numbers for your stress XX or sigma XX, okay, in megapascals. Now one thing do you notice here, that the arrows have kind of gone behind the actual part geometry, right? Now this is basically just a visual effect, because we are not using the true deformation scale factor, because we are kind of zooming in the deformation by a factor of around 347. And how do you know that? It's written over here. Everything is clearly written, right? So it's written on the top here that the deformation scale factor is 347.36. So that sometimes confuses the students. So I can change that back to either true scale factor or no deformation scale. Okay, so I can double click on this, and it will again open the same option window from where I originally plotted the chart, and in this I can go into true scale to basically reduce this anomaly, and now you can see it's now showing it on a properly scaled graph. Now, so this is the maximum stress. Now how do we know if the computer has generated results which are reasonable and correct, or have we made a mistake? Yes, exactly. So I call this first step as sanity check. Okay, you always have to carry out a sanity check on FEA models. Now keep this in mind, I'm not calling this as validation. Okay, I'm calling it as a sanity check. Why? Because for validation you need to have a comparable level of accuracy in the other method as well, right, in which you are going to compare. But if you are going to have all the calculations with the same level of accuracy, then what's the point of doing the finite element analysis, right? In this simple example, I can actually even do a full validation as well. Okay, but for more complicated real life problems, like if you are modeling an engine block or a chassis, it will be very difficult to do a full validation. Rather, it will be sufficient to initially do a sanity check to basically validate the results, some of the key results about which you can be sure through your simple hand calculations. Now, in our simple hand calculations, which calculations we are 100% sure of that they are reasonable, they should be reasonably accurate despite our simplifying assumptions, right? So the stress that we calculate as gross stress, right, which is away from any of the concentration points, right, that is, we reasonably expect that that number should be correct in our hand calculation, right, because there is no big change happening, the loads are applying in a normal manner. So that's why I will use that number. So what was our gross stress in this case? Let's quickly go back and see our hand calculations. So our gross stress from our hand calculation was 55.07 megapascals, right? So this was our gross stress. So I will basically do a sanity check, right? Gross stress from hand calc is 55.06 megapascal. Now, in your FEA, which portion of the model should have the value similar to gross stress? Anywhere, either here, right, or here, away from the concentration points. So how can you check this number? Obviously, you are getting this green. Now, if you look into the legend, that can be any number between 80 and 51, isn't it? That green shade that you are seeing here. It's difficult to tell, isn't it? So we need a more accurate way of finding this out. So to do this, we go on to plot tools. In the plot tools, you go on to probe function, okay? In the probe function, you click on the probe and then you click the probe anywhere on your model, and if there is a node around near that point, it will select the nearest node, because I remember I told you it's calculating everything for a node, okay? So right now the software is showing you the nodal value at node 508, okay, which is, it's also telling you the location, and it's giving you the value to be 55.02 megapascal, okay? So I will say that from FEA analysis, away from concentration points at node 508, and location was what? Location was 141 in X and 20.4 in Y, okay? So X is 141, 20.4, and Z is 12.7. That's okay, the Z is same throughout, okay? Value is 55.02. Now this value is within 5%, or actually less than 5%. Right now this is probably even less than 1% error, right? So this gives us confidence that our model has been set up correctly, okay? If there was a fundamental flaw in the model, then this number would be off, okay, by maybe 10%, 15% or something like that, yeah? So this number would be off. So that means that is our basics first sanity check. The second sanity check that I can do on the model is by looking at the displacement, but I will do that in a second afterwards. First, now because I am confident about my stress numbers, I can also read down the maximum value of the stress. The maximum value of the stress in this case is 108.51. Now keep this in mind. I do expect you to carry out a sanity check on in your project as well, okay? Because otherwise, if you are getting numbers which are completely different from your hand calculations, then what's the point, okay? So you have to do a sanity check in your project as well. Right. So now we have noted down the maximum value of the stress. Now, what's the displacement now in this case? So how do we get the displacement? Anybody? Just like we did for the first chart. We created a chart, we went on to the results, we right clicked on it. Yeah. First we said define stress plot. Now we can say define displacement plot. If you need strain, you can say define strain plot. Okay. So I will go and I will say define displacement plot. And in the displacement plot, again I have to select first of all what component of the displacement. So right now in my hand calculations, I was not calculating resultant, I was calculating simply x displacement. So I will plot the same here as well, because to do my sanity check I need to measure the similar quantities, isn't it? So I will say here displacement along x axis. The units are millimeter, and again this time I will already put it on true scale so that I am not confused. Okay, so I don't have to correct it later. So I will say true scale, and then in the chart option I will say show min and show max. In the numbers, again if you want scientific you can have it in scientific, but because I've already chosen millimeter as the unit, I will keep it at floating with 3 points of decimal, which may be sufficient in this case for accuracy. But look, because displacement can be very small for these kind of analysis, so maybe better to keep it scientific as well. So it's up to you which you choose, but right now I will try first with floating. If I'm not happy, I can change it to scientific. So I'll click on the green tick and it will now plot the displacement for me. And can you see here that the displacement which is maximum is 0.048. Okay. So now my second sanity check can be, I can go back to my hand calculation and look, what was my total deflection from my hand calculation? 0.0472. So I will say, so this was my first sanity check. Okay. And now my second one will be on the displacement total along x axis from hand calcs is 0.0472. Okay, and from FEA analysis, total displacement. Now this is not for a particular node. Okay, this is total displacement along x axis is equal to 0.048. Right. So again, if you want to calculate the percentage difference, you can simply say 0.048 minus 0.0472 divided by 0.048 multiplied by 100, and you'll see that you'll have less than 1%.
So we can change the other digits like 0.049 or.
Yeah, you can if you want to change the decimal places, you can increase more if you more accuracy, right? So right now, so this means both stress and displacement have less than 1% error, difference I would say, I will not call error. So the model is set up correctly. Now that we are happy with the basic setup of the model, right, now we can basically start to worry about other quantities. Yeah, and what other quantities? So basically, look, so here the displacement was how much? 0.048 mm. Okay, now in this case, how will you calculate the margin of safety from this analysis, FEA analysis? How will you
We have
calculate
over
margin of
actual.
safety?
What we have over actual. So the one from the website, the one from the Solidworks, over the one we calculate.
No.
The opposite. The opposite.
Yes, factor of safety, because I use the same definition for margin of safety and factor of safety.
Okay.
Yeah.
The strength over the calculator.
The actual maximum stress, right?
The
So
actual maximum is what we calculate. Right?
yes, so the strength, not the hand calculation. What is the strength in this case? Anybody know?
It was good. The AISI 1020
Yeah.
strength.
So how will you know what the strength of the material is?
I think from God.
By actually looking into material database, isn't it? So you can go and you can see the strength of the material. Okay, so the strength of the material from strength of in this case my material is AISI 1020 steel, right, is equal to how much? So how do we know that? Let's go back to our initial, right, where we assign the material, right click on it and again apply edit material and now read the value. So in this case you can either use yield strength or tensile strength, right? So which one should we use? 420, that is the tensile strength, right? Now this depends on your objective. If you don't mind it becoming plastic, then you will use tensile, right? Yes, because in our case we don't even want it to become plastic, right? So we'll use yield strength. So because the tensile strength is the ultimate, okay, so we'll use 351.57. so that is our 351.57 megapascal from Solidworks. So that's our yield strength. So now for our factor of safety, what we have to do is we have to take the yield strength, which is 351.571, divided it by this number. By the way, which number it should be? Let me ask you here. So if you go back to the stress plot, normal x, right? So it should be the maximum number from this graph, and it is 108.51 in this location. So it is 108.51, and this is telling you that the factor of safety in this case is roughly how much? Can somebody tell me the calculated number, please? .23, right? So 3.23 is the factor of safety in this case. Now the question is this how can we be sure that this number that the software is calculating as the maximum is actually correct, or it is truly correct? Yeah, because right now we can also compare it with our chart method, right? But I don't want you to do that, because in real life situations you may not have, you're trying to do the analysis and the kind of feature that you're looking, it may be difficult for you to find the correct charts. Yeah, so how do you work out? You can do the basic sanity check, you have already done that, but then how can you be sure that the maximum stress is being captured correctly? The simple answer is you cannot be sure unless you do what we call as a convergence study, okay? And that is now what I am going to do, okay? So I will basically rerun the analysis with different mesh sizes and try to see if the number of this number of the maximum stress, does it change significantly or not with the change of my number of elements and number of nodes, okay? So basically what we will eventually try to do is we will basically rerun it for these 1, 2, 3, 4 cases, and then we can plot the results on a graph to see how it is attaining a plateau, okay? And now rerun the analysis. Now, how do we rerun the analysis? Before we proceed, let us actually save this file by clicking on there on the save button, so that whatever you have done the analysis so far, the results are saved. Now, instead of overwriting the results, because I want to again compare the results with this analysis, what I will do is I will rerun the analysis by copying the simulation file. That will make it easy for us, because we just have to then change the things that we want to change and not change everything in the model, right? So to do this, we can just right click on this. Can you see here? Yeah. So where the name of the study is written, draft mesh default size. Okay. So right click on this and say copy study. Now when you say copy study, it gives you the name of the source, which is correct, and then it says what is the new name that you want to give it. Okay. So the new name that I want to give it will be high quality mesh, and I will actually first run it with the course size. Okay, with the course size. So I will say high mesh course size. Okay, so I will keep all the other things same, no other change, and I will click on this icon, green tick. So now this has copied the whole model, and you can see here it's got everything. The part material is still the same, the boundary condition is there, the force is there, but the mesh is no longer there. Okay, so we can recreate our mesh. Okay, at this stage, if you wanted to, for example, change the material, you could have done that as well, but I don't want to change the material right now. I just want to change the mesh. So let's now again say create mesh and run. So it will say this will delete the existing mesh. We'll say yes, no problem, and we go into the mesh quality, move it back to high quality, which was the default behavior. Okay, so this now gives us more number of nodes for each of the wedge. So now the number of nodes are no longer just limited to the vertices.
Definition, did you change anything?
And in the definition, instead of having it in the middle, which is the default, I will move it to coarse. And in the mesh parameter, I'll still keep the standard. And you can see the element sizes are actually even bigger this time, right? So you may be thinking, well, if you are reducing the number of elements, then maybe the results will even become worse. But the thing is, we are also changing the quality, right? From draft to high quality, which means that although the number of elements are becoming less, the number of nodes may actually be even larger still. Okay, and this is what we will observe. So let's just click on the green icon, and you can see here clearly the number of elements is bigger, and it actually took even less time to create this mesh. But now if you go and right click on the mesh and click on the details, you will notice that the total number of nodes has gone up to 1902, right?
Crushed.
It's okay if you can reopen it if you've saved it in the last step. Okay, so if you have saved it, you can always reopen it. All the changes will be there. So I mean, you can focus, Hassan, right now on the process, and then you can repeat it later as well, because you'll have the recording. Okay, so don't worry about it too much. Let's because I know there is only like maximum 20 minutes left in the class, so I want to finish it before we move on. So you can see I have noted here the number of elements is number of nodes is 1902, but the number of elements is 1027. Now this is interesting, because now for lesser number of elements you have got bigger number of nodes. If we now rerun the analysis, okay, and if we rerun the analysis, because we have copied over the files, you can see by default the von Mises is there and displacement, but what I am interested in is the stress which I created, right? The stress X. So can you see it on the screen? This has now been updated with the new results. And did you notice something? That the maximum stress has suddenly gone up to 159, and its location has also slightly changed, right? So this is a big change, isn't it? So if you note here, we have moved from 108 to 159. So that means there is almost 50% change, right, in the values. So this is significant. It means we can't just ignore it. It means there is, in the previous and in this case, there is definitely a mesh effect, right? So we have to further study this. Similarly, if we look into the displacement, by the way, again you can do the sanity check as well, but right now I'm ignoring that because I'm using the same copied model, so there is little chances of any other thing changing. But if you want to do the sanity check and you click on the probe, you'll see that the gross stress is still around 55.02, which is very similar to the previous case. So what it is showing you that it's not because of a fault of your setup, it's purely a mesh effect, right? It's purely because of how the calculations are being refined more closer to the concentration point.
And sir, what we rely on, which like strength or which
Mesh.
Yes, which mesh?
That's what we are going to find out by doing this convergence study, right? It depends on how much accuracy we want from our analysis. Look, if you have a very complicated, huge part and you try to use a big number of elements, computationally you may not be able to solve it. Right now you will be able to solve for all of these cases, right? But so practically it's basically a judgment call, right? But doing this allows you to see what kind of difference is happening, because you see eventually what I will be showing you is here. Can you see next step when I make it and I just change it to default, then there is a change, but it's not as significant, right? In the next step there is again a change, but it's also progressively becoming less and less significant, the change, although you will see that the computational cost will increase, okay? And so basically you will be converging to a unique output, okay? So and then you can decide. Now I will also show you a way of reducing the computational effort by just focusing on dense mesh near the point of interest, because we understand right now the problem is with the concentration points, isn't it? So basically what we can do, and you can also check for the maximum displacement in this case, okay? And the maximum displacement in this case is coming out to be almost same as the previous case, which is interesting. You know why? Because that is showing you that because the stress concentration is only on a very narrow region, it's not affecting the overall displacement change significantly. So if you were only interested in knowing the displacement from the analysis, then even the first analysis was sufficient, isn't it? But if you are interested in knowing precisely the amount of stress, then naturally you have to go for at least a high quality mesh. You can't rely on a draft mesh in this case. But let's rerun the analysis a third time, and this time if I again copy the simulation and I will call it as high quality default size. I'll keep the rest of the options same, and again in the mesh I will create, and when I create I will delete the old mesh and I will basically just simply move this slider to the middle, keep the rest of the mesh parameters same. This changes the number of elements. I click on OK, and you see now the mesh is more refined, okay? And if I now go and check the mesh details, I see that I have got 6,444 elements, which is same as the first analysis, but the number of nodes is now much higher. It is 10,627, okay? So it is 10,600. So this is the case now that I am dealing with, okay? But you can see here that initially it only had to solve 1,600 equations, then 1,902 equations, then it is solving an additional almost 8,000 equations, right? But then by solving 8,000 more equations, the results will only change 10 megapascal. Previously they were changing almost 50 megapascal, right? So previously the effect on the results was huge. Now the effect on the results is becoming less. So really as an analyst you need to decide that how much more computational power you want to use, isn't it? Because you can keep on increasing the number of equations, but then you may not be getting so much benefit, right? and that's what I will demonstrate in my fine quality mesh next time. But right now just let me replot the results as well. So if I rerun the analysis, you can see here now it's taking, can you see here, it took a few more seconds, right? So to solve. And again, if I go back to my stress plot, you can see here the stress has gone up to 169.6. Again, the gross stress will still be very similar, right? So it is still 55.02. So that means our analysis is correct. It's just the stress concentration which is really the affecting. Can you see now the stress concentration is clearly being defined in this region, right? So this is the problem issue. So now we compare these results and we can look into these results, and we can also calculate the, by the way, in the same way, the factor of safety. And can you see here, each time the factor of safety is also changing. But you can see here the change of factor of safety was huge. Here is only minor change, right? And next time when I change it again, so I'll rerun this again a third time, and this time when I run it, I will call this as high mesh and fine size. Okay, all the other things are being kept same, and again now I will remesh it, create mesh, and I will basically just simply move the slider to fine. I'm still keeping the same high quality, keep in mind. I'm just moving the slider to fine. I'm keeping the same standard mesh size. You can see that size has now reduced to 2.13. So that means the total number of elements will be huge now. Can you see here? It has taken it even more time, and it is now very, very fine mesh. Okay. So in traditional old computers, even this level of the mesh may actually cause it to your computers to crash. Okay, but I think our computer can handle it easily still. Okay, so let's rerun the analysis. Okay, so if I rerun the analysis, you can see here it's clearly slower. It's taking 4, 5, 6 seconds, almost 7 seconds, right? Why? Because now it had to solve how many equations? 80,860 equations, right? So that's how much computational effort is being input. Okay, yes. So it's a bit too much. If you think about it, this is just a small part. If it was like an aircraft wing and you had this kind of mesh, no way you will even crash the supercomputer.
Yes.
Right?
So 80 million.
Yes. So that's why you need to think about these things carefully and decide what will be the acceptable level of the analysis refinement. Okay. So in this case now, but again in big parts, if you really are interested in, so this is now the case that I just ran with the high quality mesh 80,000, and the highest stress came out to be 177, right? And the displacement is hardly changed. So for displacement, all of these are okay. Okay. Now, the factor of safety has gone to around 1.98. So we know that in this case, its factor of safety is roughly around 2. Now, what I will show you next is a clever technique. Again, maybe in this small part, it's not very important to use that. But think about it from a practical point of view. You're doing a full chassis of a car, right? That will have so many holes like these in different places. You can't go on and mesh it with this kind of a mesh, right? Because it will crash your computer. So what do is you selectively mesh, okay? So when I say you selectively mesh, what it means is that just because you see the problem region is here, right? So if you can make the mesh more refined here and leave the rest as normal, then that's a win-win situation, isn't it? Yeah. And this is called as selective meshing, or basically there are several ways to do it in different softwares. Solidworks provides a built-in easy way of dealing with this situation as well. So I will do that right now. But before I just forgot to mention one point in the start. You see, we also calculated the net stress value from our hand calculation. But if you probe in this region, you are not going to find one unique number over here. Okay, so for example, here it's like 64, here it's like 72. So that net stress value is never actually present in the model, because in reality the stress concentration profile makes it, you know, different in different locations. So net stress is really just an average sort of a measure that can help you get the idea about the maximum stress, but it's not a true representation of stress in that region. Okay. So let's now go back to the technique that I was saying. So if I rerun the analysis one final time, and if I copy it again, and I will call this as high quality and controlled mesh. Okay, high quality control mesh. So how we control the mesh, I'll explain it to you. So when I click on this, I will again go back to the mesh. Okay, but this time if I click on apply mesh control, okay, it's giving me certain options. And actually what I will do is I will first I will remesh it before I do that, because I don't want to apply the mesh control on the fine size, because that's already too fine. Yeah, so there's no point. So what I will do is I will create the mesh first by deleting the old mesh. I will move the slider back either to the default or to even the coarse side, right? I can even move it to the coarse side to save maximum computational effort. And I will click on OK. It is now just same like the third case that we did. But now I will do something clever, which is I will right click on it and I will go and I say apply mesh control. And in the mesh control, I can basically give the element size which is going to be applicable. Now I can either even make it more refined here, or I can make it less refined depending on my need. For now I will just keep it in the default, which is equal to what I was getting in my very fine mesh case, right? And that is 2.13. And then this ratio determines the transition. So this ratio can be, I have used 1.5 in this case, so I will use the same, but you can play with this ratio to basically understand how the transition will take place. Basically this is there is actually a mathematical formula in the book that I have given you, you know, the PDF. It explains the formula. So it basically explains to you how the element size will change from that smallest element size to become the biggest. So it's kind of ratio. Okay, so you can look at that formula, but right now I'm using the ratio to be 1.5. So it means it will change by that factor of 1.5. So now when I click on OK, before I click on OK, I have to tell it where I want the where I want to apply the mesh control. So I want to apply the mesh control on this edge, so I'll use control while clicking the mouse on this edge and on this edge, right? So these are my interesting points. Also I need it on this edge, this edge, this edge, and this edge, right? So these are all of my control points. I have selected the face by mistake, so I'll just delete that face and I'll just keep the edges. Okay, now when I say OK, it is now selected the control points. Okay, I think I could have even selected this top edge as well. So yeah, let's also select that, because otherwise it may not be. So I will just go back, control, and in the control, okay, this is already selected on that side, but I think this edge was only left. So now it has selected all the edges. Yeah, right, I can see they are all selected. So click again. Yeah, right. Now if I remesh it, okay, and if I say create mesh, or I can just say mesh and run, right? I'll say stick with this coarse mesh for the largest size. It will automatically move it to the smallest. Now you can see, can you see here the difference? So the mesh is much more refined near our concentration point. It's usual at the far end. And in this case, if I go and check the details, what I will get is that I will have 4024 nodes only, right? So I've got around 4024 nodes, and the number of elements is 2283. Okay, so slightly different. I've got slightly different numbers here because maybe I used slightly different mesh control or some other parameter when I was noting it down. Okay, so right now it is 4024, right? And what was the number of elements? 2283. Okay, 2283. So just with 4000, let's see if we can get good results or not. Yeah, so if we now run it, you can see it will run very quickly. And now if I go and plot my normal stress, can you see here that the maximum value is coming out to be 176, which is very, very close. So it is very, very close to this number, isn't it? What do you think? So it's almost it. So now with just having 4000 elements, but place them in the equations, but having them in the right locations has allowed me to get the same level of accuracy without having to solve 80,000 equations. Right? So if you have a large part in real life situations, this is how you can deal with that. Refine the mesh through mesh control in regions that you want to have higher mesh, leave the other zones with a coarse mesh, and you can run bigger analysis.
And sir, for the project, can we use like the first and last one only, or I have to do it?
I mean, you can, as long as you show me that you have that sense of having a converged mesh, that's fine. You can use the first and last maybe, yeah, and discuss it, right? I don't want you to do a full convergence study. In real analysis, you will always do, because you'll have bigger parts, so you may do the full convergence study for one smaller part and then leave it for the rest, yeah. But in your case, yeah, it's okay. You can just use the first and the last. Okay, so you can see here that now the factor of safety has almost converged. Now in the step-by-step guide, there is also a graph plotted to demonstrate this later on, and you can do the same here as well by taking these numbers in Excel. I'm not going to do that now. I think we have run out of time now. So, but you can. I'll show you here. So graph like this. So this is called as a convergence plot. Okay, he's doing it for von Mises stresses, but I'm doing it for sigma x. Okay, because I've not explained to you what von Mises stresses is. I will be explaining it to you in either, I think, the next lecture, not today, but hopefully next 1 or 2 lectures I will be explaining that, what it is. And then we can also get back and see these results in more detail. Okay, I hope it's clear. Like I said, all the information is already available in the form of these video tutorials as well. So if you feel like you need to revise something, you can go back and check. Thank you very much.